Here?
For this one, yeah.
What was the homework?
Char at index of reverse.
Oh, like write a bunch of functions in our superstring, right?
Yeah.
So yours sucked? What's on?
I'm gonna just.
Yeah, just
It wasn't my proudest work. I'm not gonna say that.
was it because of lack of effort or lack of intelligence?
I would say a little bit. I would say lean on the intelligence part. I guess some of it just didn't click.
No, okay, well that's okay. But you worked hard at it then.
I tried, but like.
That was the right answer, by the way.
What?
It was the right answer for you to work really hard at something and not quite get it.
Yeah.
That's like kind of my preferred approach.
And I'll say I work hard at it, but I don't think. But I mean, like I might sometimes when I work hard at stuff and just consistently doesn't work, I might get a little ragey and just start removing stuff.
Well, that's okay. So it legitimately bothers you that you didn't quite get it.
Yes.
Yeah, that's good. That's exactly where a student should be.
Okay.
Yeah.
Why?
Why? Because that means you actually care about learning. Why? If everybody, if you already, but if you already knew the stuff, wouldn't it be a waste of time giving you the homework? I mean, you should be challenged by the homework.
But still, I think exploring more in the libraries and looking what kind of solving the problem is better than actually going to reinvent whatever is already existing. Potentially.
Well, except reinventing things that already exist there forces you to solve problems that you already understand what the output should be. So it works in your logic, because the logic is the thing that programmers need to work on. That's the problem-solving piece that programmers typically are not very good at. You know, they can copy code all the.
It's not copy code, like jar add. It's literally fundamental. I don't think you can just go and write something unless you're gonna write it.
They wrote it. Why can't you write it?
Well, I'm in 250 right now. So.
To be fair, they had access to value, but they decided, hey, let's make value private so no one else can use it.
Yeah. Yeah, but see, those are all good things because then that kind of falls back into that category of, you know, you're like MacGyver. You're having to solve problems with this very limited tool set. And what kind of creative things can you do? And if you get used to solving problems that way, then, you know, you regularly will get backed into a corner. As long as you technically have enough tools in the garage to possibly solve the problem, you might not do it in the most efficient way. You might not even do it in an intelligent way. But you can somehow patchwork something together. Okay, so let's look then at superstring. All right, so we're supposed to write char at. So first of all, our superstring is implemented as a class that wraps around a field. So we talk about what are objects, what do objects consist of? So objects are collections of So what are the three things that encompass an object? What are the three things we might find in an object? We possibly haven't mentioned these three. Well, I know last semester we did, but it's possible this semester we haven't mentioned them right next to each other, but we've definitely talked about the individual parts. So what are the three things we might find inside of an object? Okay, you might find methods in there. What else?
Variables.
Variables, what are they called inside of objects? What's this guy called?
Based on what you just said 5 minutes ago,
A field. Okay, so fields, variables, same thing, but typically when we call something a field, we're thinking about their global variables within the object. Okay, so we have methods, we have fields, what else? What's the third thing? Constructors. Okay, so in Java, how do we know something is a constructor versus a method? So this first thing is a constructor, the second thing is a method. How do we know? Okay, so constructors share the identical name to the class, case sensitive and all. What else? Well, that's kind of what they do, but you could initialize stuff in a normal function, a normal method as well. So what else does every single constructor not have that every single function does have? A return type. Why is that? Why don't constructors have return types? That's a good question. Why? What's the return type of a constructor? Coming here, we're creating a superstring, right? Isn't this our call to the constructor? What kind of value does that guy return? Okay. The constructor constructs an object, constructs a instance of the class, but what does it actually return? Pointer, memory address. Okay. Now, in this line right here, what's the telltale sign that we're dealing with memory address? The new keyword, this guy right here. Now, you will always, 100% of the time, find a call to a constructor following the new keyword. So 100% of the time, constructors return memory addresses. With that in mind, doesn't it make sense from a convenience perspective that the folks at Sun Microsystems went ahead and said, you know what? Since this guy always returns a memory address, why don't we just omit the return type for constructor since we already know what it is? That makes sense, doesn't it? Now, some older languages, though, don't do that. Tell me about this keyword here. What is this? It's how an object refers to itself or within itself. Now, where are we defining this? What is this equal to? Okay. You've gotten the same thing wrong twice. Before you said it returns an object, and now you said it's equal to the superstring object. What's it actually equal to? If I were to print out the value of this, what would I get? The memory address. So this holds a memory address, which points to the actual object, right? Okay. Where are we setting that memory address? Are we setting the value of this, or is that automatically happening for us? Anywhere in here, do you see me saying something like this is equal to something? Okay, well, there's lots of keywords, but it's getting set for us, right? Java's setting it for us. So that just makes sense. So, because this always is going to be a memory address. And Java is always figuring out that memory address for us. So much so that they've actually removed the value, the return type of a constructor, because it always returns the memory address. It always returns the value of this. Now, would it make sense for that to work for every language? Would every language work that way? For us, it seems like that's just a no-brainer, right? If constructors always return memory addresses, and if all object-oriented languages have something like this in it, what was Python's equivalent of this? Self. We had something called self. Same thing, just a little bit different variable name for it. That held memory addresses as well. So if all object-oriented languages have constructors that return memory addresses, and all object-oriented languages have a variable like this or like self, shouldn't all object-oriented languages be able to set those things up for themselves? Not rely on the programmer to actually write the stuff? Sure. That would be something that would be nice if every single programming language did, but not all of them do. As an example, if I show you the equivalent, so I'm going to go ahead, I'm going to write a see if it'll let me take these lines out in the middle. I'm going to write the equivalent looking constructor in a different language called ObjectiveC. Okay. One of the reasons why I like to use examples from ObjectiveC is ObjectiveC tends to be very archaic. take all those things that Java doesn't make us write. Objective-C makes you do all those things. Okay. Well, but ObjectiveC 2.0 came out after that, and they didn't add those things in. Kept it the same. So if I'm writing the constructor, the superstring constructor in Objective-C. Now, first of all, I'll say that constructors in Objective-C do not have to match the name of the class, but I'll go ahead and make it match the name of the class just for consistency, okay? So we're going to say that this guy So that is the equivalent constructor in Objective-C. Now, first of all, does this look horribly foreign to us? Or it looks in the similar ballpark to Java, right? But we see a couple of interesting things here. First of all, our constructor has a return type. The return type is something called an ID. All right, in an older language, this might have been something called a void pointer. All right, but in this guy, it's an ID. Now also, just for the sake of completeness here, Objective-C starts their functions off with a little dash if it's an instance method, and a plus sign if it's a class method. So instead of static or non-static, they use minus or plus. Don't worry about that. It's not part of this example, but just kind of future knowledge. All right, so the parameters here, it's taking in a parameter named S, and that guy is of type NSString pointer. Who cares? It's taking in a string. So relatively speaking, these two top, the headers of these two constructors look very similar with the exception of this guy has no return type, this guy does have a return type. Okay? Now when we get into the body of the constructor though, we see that Java's version of this guy has one line. Objective-C's has three. Because what's the very first thing that Objective-C does? It sets the value for self. And what's self equal to? Well, it calls upon his parent's constructor. And his parent's constructor is actually an NS object, similar to what we talked about last time with Java, where all objects, if we don't explicitly say it inherits from something else, comes from the base object called object. That make sense? Okay. Are we missing a bunch of people today? Like a whole bunch of people.
Like, there's like 2 people. It feels like that.
No,
spread out.
but there's more people in this class than that.
16, I thought.
Yeah.
14.
There was?
Like at least 3 people.
Huh. All right. So in any case, now in Objective-C, we would have to define that we are extending something. It's not optional. We have to say extends NS object if we don't actually say extends. You put 2 little dots like that and say NS object if you're extending it in Objective-C. Not important for us. What we're focusing in is on this. So in an older language like Objective-C, not only do we give a value to self by asking our parent to go ahead and create an instance of itself and give us that baseline, we also then return the value of self, which will be a memory address. So we're responsible for this line and for this line, even though 100% of constructors will have the first line and the last line there. Does that make sense? Now, it is possible for us to, in Objective-C for us to say, oh, well, I actually want to call a less generic constructor of my parent. Because at the very top of the line, we wrote this last time, we said that when we look at the breakdown of objects in Java, at the very top of the hierarchy, we have this very generic object known as object. Okay, that's something that all object-oriented languages have in common. So there has to be a beginning. Okay, so all object-oriented languages have defined a generic object, usually called either object or NS object, something like that. Okay, at the very, very top. And all other objects come from that guy at some level. They might be a direct descendant or, a great-grandchild, but they come from that level at some point. Okay? So, sorry. With that in mind, this object guy in Java has a generic constructor that takes no parameters and does the basic stuff. So what we would see in Java is something like this. We would say this is equal to super, like that. Okay. Now Java doesn't let us do this. We hover over this that says that that this is not a variable. It's something special in Java. They've protected that guy. Okay. But we could call upon our parent's constructor if we were doing something other than a generic object. We just wouldn't set it back to this. This would automatically get augmented. So we'll see this eventually, but if we do want to call upon a less generic constructor of our parent, we would say super and then pass it if it took 2 strings or something like that, we would pass it a couple of strings here, and then magically it would do the logic of getting this updated to be that new constructor value. Okay, so if we're going to do that, it must always come first in your constructor. And I'll explain that again when we have some context for it, so don't worry about memorizing it at this point. But Java does have a way of calling a less generic version of the parent's constructor, if it makes sense for you. All right, but in an older language like Objective-C, we are responsible for giving a value to self, and then ultimately we're responsible for returning the value of self, even though those two things are things we would always do. Make sense? So once again, this is evidence of things that Java has done to streamline the developer's job so that we can focus on solving problems rather than a whole bunch of extraneous code. Now, the problem with that as I see it, a goal of a lot of modern languages tends to be type less stuff. Now, in general, I'm okay with that. Where you don't want to have like these big necessary lines that are just completely meaningless, right? I mean, you don't want to feel like your programming language is forcing you to type essays every single time you write some code. But there is such a thing as not typing enough stuff. So is this really that much worse than this? Is 2 extra lines really that big of a deal? The end of the day, not that huge of a deal, right? Now we should say, well, if these lines are always there, does it make logical sense for us not to be forced to write them? Go ahead.
Well, the question is, are they always there? Because I can see several edge case scenarios popping up where you don't want to type exactly that. You want to type something slightly different from that, either getting your, like you said, using a different constructor, or maybe getting it from a different class or some other.
You're right, but Java supports those too.
Okay.
Yeah, so just keeping in the simple case here, I mean, you are right, but Java does have facilities for those, which I think maybe is even related to what I'm asking here. So keeping it in the general sense, are these 2 lines, if we say that 95% of the time, these 2 exact 2 lines are what we'd have there, this first one and this last one, would you prefer to write them or not write them? And why? It's actually a pretty important question. How many of you would prefer not to have to write anything you didn't absolutely have to? That's a kind of a good human answer, right? Why do something that we don't have to do, every single time? Okay. So, for instance, now new cars, right? A lot of new cars have the push button, start. You don't have to put the keys in the ignition and twist it. Why should you? You can just get in as long as the keys are with you. Do you actually have to get them out of your pocket and get it lined up and twist it? I mean, why do you have to do all that extra work? Same thing. We have, how many of you have automatic, or how many of you have manual windows in your car? A couple of people. Depends on how old your car is, right? Yeah. So when I was younger, all cars had. We had the manual, but now we find out they have push button. So unless it was a money thing where you're buying, those of you who have manual windows in your car today, it's because you were limited on a budget and you bought a used car, and right. I mean, if you go out to the lot today, go to the Ford dealership or pick your favorite car company, and you bought a brand new car, would a manual window be an option? No. Okay. They're all power buttons, right? Why should I have to move my arm to do this when I could just hit the switch? Before long, they're gonna have the whole automation thing, just like we have Siri and things like that, where we'll just say, driver side window down, and then you'll be talking to your window over and over again, and people with British accents just won't quite be able to pull it off. One of my best friends is a British guy, and him and Siri used to have a very controversial relationship. It just does not work because he's British, but he also has a really deep voice. Siri doesn't get him. Either do a lot of our friends. And my wife only understands about 30% of what he says, even though he's speaking English. Very interesting. But in any case, human nature would say we like conveniences, right? We like that. Now, on the flip side, I'm coming from a historical programmer perspective. I actually prefer this syntax. And this kind of comes back to something I said at the beginning of class today. So even though he struggled with the homework assignment, and the fact that he was upset about it is the part that I actually appreciate. Okay? That he really wanted to get it, he really wanted to work at it, and he knew there was something missing there. What I don't like about some of these modern languages is they hide so many things from you. Unless somebody eventually tells you what's missing, like some of the stuff I'm going through right now, you don't know that it was ever there. So all of a sudden, things actually seem to magically happen in the background. You don't realize some of these wires are actually connected that are important. Now, because the world is a little bit different for us as programmers. A computer programmer is not the same. Well, a computer programmer with a computer science theory background is not the same as an average person who drives a car. Okay? So now, for all of you in here who drive a car, there's probably only one or two of you who know anything about how cars work, right? We got a general idea that there's an engine in there and explosions happen, like controlled explosions, and that's how cars move. Okay? But the bottom line is, you don't have to know how to build a car and how to fix a car and all these other things in order to drive a car, right? We can functionally do that. Now, the same thing's true. How many of you have heard of like programming boot camps and stuff like that, where you can go and instead of going to college, you can go and get you pay your 30 grand or something like that to some boot camp, and they guarantee you a job at the end, and you go for 6 months or something, and some of them cost some money, some of them are free or cost a lot less money, and then they take 40% of your first year's salary, that kind of stuff, So, but what they're doing in those types of things is they're teaching you how to drive a car. They're teaching you how to write a program, not necessarily what's happening under the hood. So that puts a limitation on what you're going to learn related to programming. So from a computer scientist perspective, we're supposed to understand how these languages actually work as well. Because every now and then that's important. Because we're doing this at the professional level, right? Do you think professional race car drivers probably know substantially more about how cars work than your average driver who's pulling out of the parking lot at Target? Yeah, yeah. I mean, definitely. I mean, I don't know if every race car driver could build a car, but my feeling is they probably are, at the very least, significant level hobbyists as it comes to car maintenance and mechanics and things like that. So for us, it's important for us to understand how these things work under the hood. In fact, one of our courses that you'll have later on as a senior, you'll have 470, which is programming language theory, where we write a programming language. So you have to understand how all these things come together. And if you've never exposed to it, I believe that's a problem. So the more things that happen automatically, the more things we have to explain that, oh, there's actually magically this line there. This is actually magically this line there. So I actually prefer this syntax as opposed to the I'll do everything for you syntax. Because at some point what ends up happening is when you get so used to writing these two lines and it becomes so ingrained exactly what's happening, you are in charge of giving a value to self. Then you start saying, well, I'm tired of writing these two lines. But at that same point in time, you also understand exactly how self works. Go ahead.
So would this be more like an IDE function that we've put into a language? So like, IDEs, they have autocomplete. So is this
there's probably truth to that. Yeah, I would say there's truth to that. And Java even does this guy does the same thing. When we've written dice, we have our, and actually not dice, driver. We have our public static void main string array arg. So if I'm telling you that 100% of Java programs begin and end with main, every single one of them will have a main that looks exactly like that with one exception. Args might be a different variable name, but it's meaningless. So built into Eclipse is a way for when you create a brand new class, it'll automatically generate that function for you. I'll show it to you real quick if you haven't seen that. I would encourage you not to use this yet until you get to the point where it's just kind of meaningless banter inside your head. So if I come in here and I right click and I'm going to create a new class, and let's just call this guy test. Notice down here I can say, which method stubs would you like to create? I can say, go ahead and give me main. And then it draws main in for me. Make sense? So it'll do things like that. That's a convenience you were mentioning. That's kind of an IDE convenience. So I would be okay with that for the IDEs to do some fill in the blank stuff for you that you can start taking advantage of once you've done it so many times that you're tired of doing it. You already appreciate the convenience. I think too often what happens with us in society, not that I don't appreciate it as well, is it's sometimes difficult for us to truly appreciate the convenience something is giving us when we never had to live with it the old way. So how many of you have ever been watching TV and because you couldn't find the remote or the battery died in the remote, you decided just to keep watching whatever channel was on? At some point, we've all done that, right? Yeah, whatever, right. So you got backups to backups. My backup is I just call my wife. First, if you found do you know where the remote is? The worst time, the most pathetic times are when I'm sitting 5 feet from the table or 8 feet from the table. I see the remote on the table, but I'm already nice and comfy and reclined in the couch. And you kind of like, well, I can watch. She'll probably come down soon. So I can kind of watch this channel for a little bit longer. So something like that. But most of you, how many of you, did any of you grow up with a TV that didn't have a remote? I think we're beyond that age, right? You had a TV that didn't have a remote? Okay. Yeah, so that would have been that you had an old TV even then, right? Yeah.
Or
so
like a tiny one.
Yeah, well, but even then, I mean, TVs have had remotes since mid '80s or something like that. It was pretty common for TVs to have remotes. So most of none of you were things then, right? We're all not late '90s. We're almost to the point where everybody's going to be born in the 2000s. But in any case, so I remember when I was a kid, you would, you had to get up and turn the channel. There wasn't another option. So you never had that thing where, oh, I'm not gonna change the channel. So what you do, you just plop down right in front of the TV and just keep hitting the buttons until you were ready and where you had it where you wanted it. Well, then once we had the remotes, you really appreciated what it was doing for you, right? Well, now we have all these conveniences that we don't necessarily appreciate everything it's doing for us. And we all have that same level. I don't appreciate all the stuff that a car does because I never had to ride horseback or something like that. So, we can just keep rolling back until we have it. And for the average consumer, that's okay. We don't have to know what it was like not to have a remote in order to appreciate the fact that I can just sit on my butt and not have to get up. But as a computer science professional, it's beneficial for us to know what's actually happening under the hood because we're supposed to be the professionals at technology. We need to understand how these things work, not just be practitioners. That makes sense? That's the distinct difference that exists between people who come out of those programming boot camps that have programming as a skill set versus people who come out of college with a computer science degree who have programming as a skill set, but also have computer science theory as a skill set. That makes sense? Now, that doesn't mean you can't make money and have a good living and stuff like that with just computer programming as a skill set. But that is the distinct difference between the two. So you got to decide which of those is the skill set you actually want to have. So with all that in mind, I am a fan of this syntax over this syntax. Because eventually you get ticked off at this syntax, and that's where something like the IDE can step in and give you a convenience that isn't innately part of the language, but is innately part of the tool you're using to work with the language. So, but in any case, now we all know that there's more than meets the eye here, right? Makes some sense? Okay. So I'll go ahead and just leave that in the comment. This is a multi-line comment if I didn't explain that before. So slash asterisk, asterisk slash, everything in between is a comment. So Java's not going to process that. That's just for our eyes only. All right. So that being said, same thing's true here. We showed last time that this is not required in Java. But if I were writing that in ObjectiveC, this would be public class superstring NSObject. It would look like that. And that would be required, the NSObject part of that. And what's that doing? That's filling in the gap of this guy. That this is happening. This is required to happen. Those connections happen regardless. But in a language like Objective-C, we actually have to make that connection happen. Having something that does not inherit from object means it's no longer a functional entity, a functional object in this object-oriented world of that language. Where Java says you cannot create non-functional entities because it wouldn't make sense for you to have a non-functional entity. If you're going to create an object, at the very least, it's going to be a generic object. Makes perfect sense. But when we actually have to write it, that connection's being reinforced in our mind. Okay, so having said all that, let's look at some of these functions. So we were supposed to write char_at. So char_at returns the character at position index in our superstring. Now, our superstring currently is implemented as a string. So we're going to go ahead, we'll write public char_at's going to return a char. It's going to be called char_at. It's going to take in a int index. Now, I think it would have been reasonable. I'm going to write it two different ways here, but it would have been reasonable for you to just return this dot s dot char at index. We implemented this guy in terms of a string, therefore we could use string functions. Correct? Wouldn't this have been reasonable?
If you're using the tool that you're supposed to make.
Well, it just happens to share the same name. Couldn't I have called this function Bob and it happened to be a function that returned a character at a particular position?
No, you write it.
Huh? I'm going to write it a second way. But this would have been valid. This would have been perfectly valid because we implemented our superstring as a string. Now, had we implemented this guy as a char array, we would have had to write it a different way. That make sense? Strings are implemented as char arrays. So if we're gonna play that game, that's fine. So this is one way you could have written it, and it wouldn't have been inaccurate, but it wouldn't have challenged you. So instead, we're going to write a for loop. We need to get to bucket index of this guy, right? So we're going to go ahead and we're going to say for int I is equal to 0, I is less than this dot s dot length I plus plus. So we'll walk through that string one character at a time. Okay? And now, realistically speaking, we don't want to go all the way up to the length. We want to go up to the index number of times. Right? We want to get to that bucket. So we might define I outside of here. Give I its value there. Keep going as long as I is less than or equal to index I plus plus. That'll take I, and you actually didn't even need the body of this. You could have just done that. That'll take I on a journey through the string to get it up to the position where you need it to be. Then if you wanted to use a different function rather than char at, let's go into the string class here. Yeah, you mentioned something about a function called value.
That's the field within the string class that we want to use. There's a function toCharArray that essentially gives us the same thing.
Okay, so we could have converted this to a char array, then returned the bucket at that position. Something like that. Okay, that's fine. So you did this. You said char array C is equal to this dot S dot to char array. Well, I mean, yeah, technically at that point you could just say return C at bucket index. I mean, is that really any easier than? Yeah, okay, that's fine. That's fine. But technically, and this is fine if you did it this way, technically you've been introduced the tool called charat that lives in the string class. You had not been introduced the tool toCharArray. Technically.
But you understand what
No, I get it. I do get it. I do get it. You ended up trying to make it harder than it had to be. We were operating with superstring being a wrapper for string. So if we're solving a problem that it already contains, why can't we just use the built-in thing? If I were writing this, I would have just returned s.charat index.
So now you see how, when you said earlier that you're supposed to know what goes on the ground behind them.
But you would have had to write that for reverse. And substring, I don't think I had introduced substring to you yet, right? So if we're going about this the way that I would have written it, I would have said return this.s.char at index. That's what I would have written for that one. Because we already had a function that we had access to of this guy that solved the same problem. Great. Now if we're going to do index of, same thing. This returns the first index of C in our superstring, or -1 if it's not found. So if you wanted to write this the more difficult way, we're going to return an int. This guy's going to be index of, and it's going to take in a char C as a parameter. So you could have just said return this.s.index of C, because S currently had the guy like that. That would have been legal. And you do have access to the index of function of the string class. And we happen to be writing a function called index of the superstring class. But we also could have gone through and searched this guy looking for, using char@, to look at the current character. So we could have said for int I is equal to 0, I is less than this.s.length, I plus plus. Now, if we get through the entire string and never return anything, we would have returned a -1 down here, right? That means we didn't find it. Otherwise, we'll ask the question, if the character we're currently looking at is equal to the character that we were searching for, go ahead and return the position we found it. So if C is equivalent to this.s.char at I, then return I. Now, am I allowed to use the double equal sign here? What's the double equal sign? Equivalence operator. It's the primitive equivalence operator. So this only works for primitive types. If I compare strings using the double equal sign, what happens? What is it actually comparing? The memory addresses. It's comparing the underlying memory addresses. So am I allowed to use the double equal sign here, even though S is a string? I'm looking at an individual char of that guy. So all this stuff over here actually boils down to a char primitive type. This guy is a char primitive type. So I'm comparing two primitive types to each other there, which is fine. All right, so that's index of. If you wanted to write out the more drawn out way. Fair enough. Okay. So those were kind of warm-up ones, right? Because these guys had built-in functions and just get you used to writing some instance methods. Reverse, we don't have a built-in reverse function in string. We don't know about it, and strings don't have one of those. String buffer actually has one of them, but we didn't have access to this tool anyways. We had our toolbox sitting in front of us. So we'll say public. Now, actually notice this guy actually works even a little differently. This guy reverses the internal state of the superstring. So rather than it returning a brand new string that is the reverse of the old string, it actually changes the current superstring to be the reverse of itself. That makes sense? So this guy actually is not going to return anything because he's not returning a value. He's internally manipulating himself. So this is going to be public void reverse. Now, why doesn't this guy have to take in any parameters? What string am I reversing? The internal string. So did this guy need any additional information, or does he already know about the internal string? He knows about it. He has access to S up here. So for reverse, we're going to create a new string. We call this guy answer. Start that guy off as the empty string. We're going to spin through our internal string. We can either go through it backwards or we can go through it forwards and build it backwards. Pick your poison. So we'll say for int I is equal to this dot s dot length minus 1. That's the last legal bucket in S. Keep going as long as I is greater than or equal to 0. Subtract 1 from I each time. And what are we going to do? We're going to say answer is equal to answer concatenated with this dot s dot char at I. So we'll build up our answer in reverse. And then the very last thing we do is we change our internal variable. This dot s is equal to answer. Now, do you understand the difference between doing it this way? Let me actually just create a second version of this guy. Call this guy reverse 2. These two functions, while having almost identical internal logic, have a very, very, very different output, or different consequence might be the better way of putting it. This first one actually changes the internal structure of this particular superstring. It replaces his old version of S with the reversed version of itself. This second one does not change the internal structure of the superstring. Instead, it returns, in this case, a brand new string that is the superstring's internal component in reverse. We could have also returned a superstring here and returned a new superstring out of answer if we wanted to keep working with superstrings. But in any case, this guy changes the internal state of this particular superstring. This guy creates a new superstring which represents the reverse of the current superstring. That makes sense? So the one we were supposed to write is this guy right here. Questions about that one? Say this one does not change the internal state, but returns a new superstring. That way I'll leave it in the answer code. All right, so the last thing, substring, returns a substring, returns as a superstring the substring of the string from position start to end, not including end. So I need to build up a substring inside of this, then build a new superstring out of that substring. All right, and this guy is going to go from start to end, but not including end. So, and he's going to return a superstring. And we'll call this guy substring, int start, int end. So we need to go in and we need to build up a string first of all. That is the substring of our internal string. Then once we have that substring, build a superstring with that substring. So we'll have our string answer is equal to the empty string. Now we're going to go through and we're going to build up answer as our substring. So we're going to say for int I is equal to start. Keep going as long as I is less than end, not less than or equal to, because equal to would mean we would include end in our substring. I plus plus. Each time through we'll say answer is equal to answer concatenated with this dot s dot char at I. So we'll build up the substring that we are interested in, and then we'll ultimately return a new superstring built from answer. Like that. That one make sense? All right, questions about any of those guys? So if we test this, go out here to driver. Remind me, just make sure we have that in there. I create a new object here called S. I go and print S out. Right now, this actually prints the superstring, right? Two-string. How does the two-string thing work? Remind me. If I leave this two-string out, and I run my program, I get memory addresses. If I put that two-string back in, and I run my program, I get nice outputs. How does two-string work? Okay, so the generic object class has a two-string method in it, and that generic object knows how to print out the memory address thing. We can choose to create, we override that internal one. We can choose to create our own version of two-string, which we will hit first because variables resolve to their most local definitions, so do functions. Because actually functions are implemented like variables. It's a name-value pair. We have a variable name, it's associated with this value, which if you're in the 470 class, we call this a lambda calculus expression. Okay, so a lambda calculus expression is an unnamed function, and we associate it with a name called toString. But in any case, things resolve to the most local definition, so when we call toString, which is happening when I run driver here, and I say println, this is actually trying to call s.toString. How do we know that? Besides me telling you. If we go and look at println, we need to go to the system class, then go to the out field. How do we know this is a field? Lowercase? We'll call it 92% wrong, but you might initially suspect that it's a not a actually no, because most functions start with lowercase. So no, 100% wrong. How do we know that this guy is a field, not a function? Now, I promise you, it might feel like I'm harping on things that you think aren't important. I promise you the things I'm harping on are the most important things. Because one of these days, what's going to happen is you're going to get really good at solving problems. All right? You're going to get good at solving them, where you're not going to make the little mistakes that you're making these days. So while you need a lot of practice, reps, solving problems in all these different ways, that's true. Being able to read the documentation, being able to understand what's going on when you look at existing code is an invaluable skill set. You have to have that, or you're going to be very limited on what kind of problems you can solve. How do we know what kind of animal that is? Well, we could certainly go and look in the documentation and fish through it and figure out what it is and like, oh, that's what it was. But we can look at that right now and have a real good idea on what we're dealing with there. What's he missing? What would he have to have in order to be a function? Yeah, you need parentheses to be a function. He doesn't have those. So this guy's got to be a variable-y kind of guy. And we said earlier in class that variables, when they're associated with objects, we actually call them fields. Okay? Now, so this guy is going to be a field, assuming it's not a syntax error. It's going to be a class field or an instance field? What would you suspect? Will we suspect to find this field with a static in front of it or not static in front of it when we go and look it up in the documentation? Keeping in mind that last class I actually showed you this exact one. So I'm not expecting you to memorize it. I'm expecting you to be able to read the room, if you will. You know, look at that line and decide what kind of field is this guy likely to be. Do we expect him to be owned by the class or owned by an instance of the class? Who's calling them? System. What kind of animal do you think this guy is? Class name. Why do you think it's a class name? You're allowed to do your capitalization stuff now.
Okay. Naming convention.
Naming convention, yeah. So we look at that, capital S. Typically, classes start with capital letters. So we're going to go in here with a pretty good suspicion that we're going to find a class in there called system. Okay? So if this is the name of a class, and this guy we've identified as a field because it doesn't have the parentheses, do we expect it to be a class field or an instance field? How are we calling it? We're calling it with the name of the class in which we presume it was defined. So it's going to be a class field. So we expect it to have a static in front of it. So if I go into the system class and I go into the field section, I expect to find a variable in there named out that has a static in front of it, and it's going to have some type. Now, what I'm looking at here doesn't give me much information about what kind of type this is, other than if I happen to have memorized what type of object has a function called println. All right, I believe this guy's a print stream, but we're kind of limited at what our, the information we can gather from that one line there is somewhat limited, but there's still a lot of information there. We have a class name system. We have a class field name out. We have a instance variable or instance function named println because we're calling it with out, which we presume is an instance of some class because it's got a lowercase letter. There's quite a bit of information we can get there. So let's go in here to the documentation. We'll go to system. That's the name of a class. We'll go to the field summary. We see a dude in here named out. We do indeed find static in front of it. He's actually a member of this class called printStream. We go into printStream here. We scroll down to the method summary. We find, we'll go past the prints and go to the printlns. So we have a whole bunch of println methods. We have a println that takes nothing, a println that takes a boolean, a char array, a double, a float, an int, a long, a string, and an object. When we call system.out.println and pass it a superstring, which version of these guys is getting called? The one that takes in an object. Now, why is it that the printStream class didn't implement a println function that knew how to print superstrings? Yeah, but shouldn't they have known we were going to write a class called superstring? Back somewhere in the late 90s when mid-90s when they were writing Java, they wrote the println function. I mean, surely they would have had a big list of all the objects people would have ever made. No, doesn't make any sense. We can come up with literally an infinite number of objects. Well, probably not infinite. We're limited by the bounds of the alphabet. And we can also have numbers, and they just can't start with numbers. So there is a finite number of function names that we could create, and also class names. but it's big. So almost infinite, we can say. Okay, so what they did is they had a catch-all in here. They said, look, here's all the primitive types that we know about. All these guys are built into the language. We know how to print out doubles. We know how to print out floats and ints and longs, blah, blah, blah. We even know how to print out strings. Might as well be a primitive type even though it's technically an object type. But we need the catch-all now. What if you ask us to print out something that isn't one of those things? Well, that means you built it yourself, which means it must be something that inherits from generic object, right? Therefore, I'm going to have a guy that takes in a generic object. And what he's going to do is he's going to call whatever object you pass in's toString method. Why does he know that's okay to do? When they wrote println here, why could they assume that they would be able to call a toString method? And what does toString return? Go back to generic object. toString, ultimately, I will just show it in our code. toString eventually returns a string. Here's toString. And this guy returns a string. So if println that takes in an object calls that object's toString and gets a string, what can he then do with that string? He can call the println that knows how to print out a string, right? That guy's already been written. So he'll call this guy. So this guy is implemented in terms of this guy. He'll first take the object X, he'll call his toString method and get a string. And then he'll use that string to call this version of println that knows how to print out strings. But why is he able to rely on this object 100% definitely having a function called toString that boils down to a string? Why is that guaranteed to be the case? Who wrote this println function? That could have been a girl. An employee.
Guy is a gender neutral.
Okay, is it? I don't know if that's true.
When you say context, I mean,
I get it. I'm just,
2017, no.
I'm just,
2015, yes.
I'm just screwed around. Okay, some person at Sun Microsystems back then, which isn't even a company anymore, right? So whoever invented Java, probably a team of people. They kind of split up the functions among the people, and somebody wrote this print stream class, and in that print stream class, they wrote the println functions. Now, who wrote the object class here? Might have been the same person, might have been a different person, probably on the same team, whatever. Now, also, if you think back earlier in today's class, now we're talking about language theory stuff. I've mentioned that all object-oriented languages use this model of having a first object. Okay. Somewhere they had to create the beginning. What is the most generic object we can possibly have? And they decided in Java to name it object with a capital O, naming convention. Okay. They happened to decide in ObjectiveC, Apple's programming language, to name it NS object. Anybody know why they named it NS object? I think I've told the story in here at some point. Or it was at least in the 200 class I told it. Why do they call it NS object instead of object?
Does it stand for not some object?
Actually stands for next step object. It's the Apple programming language. And what was Next Computers? Next Computers was the company that Steve Jobs founded after Apple fired him. And it was also the company that Apple acquired once they rehired him. No, Next Computers.
Oh,
Yeah, Apple fired.
I was thinking his other.
Yeah, the other thing was Pixar, yeah. When Apple fired Steve Jobs went and founded a new computer company called Next Computers. And when Apple was failing as a company, they acquired the company Next Computers, which came with Steve Jobs, which they put in as the interim CEO. Haha, I-CEO. With that came Next Computers, and what do we have today? We effectively have Steve Jobs' Next Computers with an Apple logo on it. Hiding right in plain sight. We even see it in the documentation of its programming language. So the modern Mac OS X, Mac OS X programming operating system is actually the Next operating system with a fancy Apple front end on it called Aqua, which Next stole from OpenBSD. So you know, you just follow the line. You follow the breadcrumbs somewhere down the line.
Mac operating system 4 was not that.
Oh yeah, I mean, so if your operating system sucks, so Mac OS 9 was very, had limited differences from OS 8 to OS 7 to OS 6, and the biggest issue with it was their multitasking model. They had a preemptive multitasking model. How many of you are in 350 right now? So have you talked about preemptive multitasking? You might not have gotten to multitasking yet, but whatever, you'll talk about it at some point. They had a bad multitasking model, which caused it to be very unstable. So what do? They took an operating system that already had a really good multitasking model. They said, hey, Unix has been around for a long, long time. Let's just take that guy. And well, why was Unix not user-friendly? Well, because it didn't have a nice user interface. It was made for, real computer scientists who like to, go out to the terminal and type in all these commands and stuff like that. It wasn't made for grandma and grandpa. So Apple took what they were good at, design, interfaces, and said, we're going to put a nice usable interface on top of that unusable but really, really good operating system. Make sense? What were you going to say?
It's just a reference to, if you just keep going back, eventually you'll just get to Walter both.
Yeah, I mean, you can chase anything
Yeah.
back, and you'll eventually get to some starting point.
And then you'll get further back than that.
Yep.
Then you'll get to the first mathematician. That's interesting.
Mm-hmm. Yeah, but these become interesting storylines that, a lot of people view that Apple story as, Apple, came back from, basically almost failure and repaired themselves as a company. They actually just slapped the Apple logo on a new company right underneath their eyes. Very interesting backstory. Okay, so some person at Sun Microsystems wrote the object class. Some person, possibly the same person, at Sun Microsystems wrote the print stream class. Now, those two classes are reliant on each other. So in computer programming, we have this term called, we'll call it coupling. And actually, it's not fair to say it's computer programming. This is really a software engineering term. So most of you will be taking 370 next semester along with 300. So you'll be taking software engineering, I believe, with Dr. Locklear. And so something you'll talk about in there is this idea of objects being coupled, or the concept of coupling, where you have two objects that are reliant on each other. Now, in general, when you write software, when you're solving problems, you want things to be able to stand on their own as much as possible, right? You don't want to have too many things relying on other things, because then if this part breaks, all these other things break too. But sometimes it's unavoidable. Sometimes you're going to have pieces that are reliant on other pieces. And so right now we're looking at an example of, if you want to be able to include the ability to print out generic objects, somehow, what we're going to have to do is we're going to have to write with that in mind, the object class. So the object class included this generic toString method that says, look, if in the case you haven't done this yourself, this is what we will give you if you call toString. We will give you a generic memory address looking string that is a representation of that object. Because we're promising that, Now the person who wrote printstream can write a println method that takes in an object, and you're guaranteed that that object will have a toString function. Make sense? It'll either get the one that it inherited from its parent or grandparent or great-great-grandparent, wherever it came from. Okay? It'll either get that top-level one, or it'll get a more local one if they chose to override it. Make sense? All right, so that's where these things kind of came from. So coupling is the idea of multiple parts of a solution being reliant on each other. All right, so we come back out here, we create our superstring hello, we print out our superstring, then we go ahead and say s dot reverse, that's our one that changes the internal state of it. Then we print out that same superstring again, we'll see that guy in reverse. If we reverse it twice, we reverse the reverse and we'll be back forwards. All right, that makes some sense? All right, so now, continuing to think about superstrings before we what if, now this might not necessarily be a practical thing we might want to do, but it's still something we're going to do, just for a logical exercise type thing. So what we want to do is we want to have a function called sort that internally sorts the characters in the superstring from lowest, well, let's just say in ascending order by Unicode value. So this guy, in a simple case, so an example might be if you had HELLO, the alphabet, to sort this alphabetically, which would also be Unicode, right? Because Unicode A comes before B, comes before C, comes before D. But I'm telling you to do this in Unicode order because upper and lowercase characters will be different. So which comes first? Uppercase comes before lowercase? Yeah. So a uppercase Z would actually come before a lowercase a in Unicode. So when you sort, that's a true statement. So you can use less than and greater than and that stuff with the Unicode values. So an example of hello would be E H L L O. Is that sorted? I think so. So it should change the internal state of the superstring to be the sorted, all of its characters sorted in Unicode order. That make sense? So you have to come up with some algorithm for sorting. We did talk about an algorithm last year called insertion sort. Did we also do merge sort last year?
Yes.
Okay, we'll do merge sort again in here. But though, if you want to look back at your past notes, you can look, insertion sort would probably be the one that you want to implement. But I might encourage you to figure out how to sort it on your own. You know, just dive in and sort it. Practice with logic. But if you want to look at your past notes, look for insertion sort. That'll give you at least a starting point for an algorithm for doing it. Questions, comments, concerns, bribes. Remember, today is student, faculty, staff Bible study, Tuesdays. It's from noon to 1 in the terrace room. You get free lunch, God in grub. Just go down to the cafeteria, sign in. You don't have to swipe in or anything. Grab your lunch, take it down to the terrace room at noon. And I will get up I'll put the Bible homework up here in about 5 minutes or so. So you'll have that as well as this new assignment. All right.